Human-made climate change is a moral issue. It pits the rich and powerful against the young and unborn, against the defenseless and against nature. Climate change is a political issue, but politics fails when there is a revolving door between government and the fossil fuel industrial complex. Climate change is a legal issue. The judiciary provides the possibility of holding our governments accountable for their duty to protect the public interest. There is a huge gap between what is understood about global warming by the relevant scientific community and what is known about global warming by the people who need to know, the public. It is difficult for the public to recognize that we have a crisis because human-made global warming so far is small compared to day-to-day weather fluctuations. Yet the fact is, we have an emergency. Because of the great inertia of the ocean, which is 4 kilometers deep, and the ice sheets, which are 2 to 3 kilometers thick, the climate system responds slowly to climate forcings such as increasing greenhouse gases. But this inertia is not our friend, because it increases the danger that we may pass tipping points, beyond which the dynamics of the climate system takes over and rapid changes occur out of humanity's control. The bad news is that atmospheric carbon dioxide, CO2, has already reached a dangerous level, having increased from 280 parts per million 200 years ago to 389 parts per million today. The good news is that it is still possible to get CO2 back below 350 parts per million if we act promptly. And there would be many benefits of taking the actions that are needed. The great ice sheets on Greenland and Antarctica provide examples of tipping points, especially the West Antarctic ice sheet, which sits on bedrock below sea level. If an ice sheet is weakened to the point that it begins to collapse, the dynamics of the process takes over. It will be out of our control. We cannot tie a rope around an ice sheet that is 2 kilometers thick. Extermination of species is another nonlinear problem that can accelerate because of the interdependencies among species. Multiple stresses may cause enough extinctions that ecosystems collapse. Methane hydrates are essentially frozen methane. If they begin to disintegrate rapidly, it could become a self-sustaining process. These tipping points all have occurred during Earth's history in conjunction with warming climates. Following mass extinctions, new species evolved, but it required hundreds of thousands of years. We will leave a much more desolate planet for future generations if we destroy many species. Climate inertia and tipping points give rise to potential intergenerational injustice. Today's adults enjoy the benefits of fossil fuel use, but the impacts will be borne by young people and future generations. Our parents did not know that their actions would affect future generations. We do not have that excuse. We can only feign ignorance. It's called denial. let me, I showed this photo of our first grandchild in 2000 because newspapers had called me the grandfather of global warming. That actually was not true. There were other scientists who had talked about global warming long before I did. But I thought it was amusing to show that I really was a grandfather. After I testified to Congress in the 1980s, I had decided to stick to research and leave public communication to others. But by 2004, we had 2 grandchildren, and the gap between what was understood about the science and what was known by the public had become huge. I decided to give one carefully prepared public talk in 2004. The talk was titled Dangerous Anthropogenic Interference, a discussion of humanity's Faustian climate bargain and the payments coming due. I began with this chart comparing Mars, Earth, and Venus. Mars has a thin atmosphere of carbon dioxide. Earth has an intermediate amount, and Venus has a very thick carbon dioxide atmosphere. The greenhouse effect of carbon dioxide, the fact that it allows sunlight to penetrate to the planetary surface, but partially traps the planet's infrared heat radiation, causes each planet to be warmer than it otherwise would be, given the amount of sunlight that it absorbs. Mars by a few degrees, Earth by a few tens of degrees, and Venus by several hundred degrees. Mars is too cold. Its water is all frozen. Venus is too hot. The water has boiled into the atmosphere. Earth is just right for life to exist. The habitable zone around a star is the zone where liquid water can exist on a planet. Our sun is an ordinary star burning hydrogen in its core, producing helium by nuclear fusion, slowly getting brighter. When the solar system was young, the sun was 30% dimmer than today, and the habitable zone was closer to the sun. Venus was cool enough to have an ocean. Earth was near the cold limit of the habitable zone. On several occasions, Earth froze all the way to the equator. The most recent snowball Earth occurred about 700 million years ago. As the sun brightened, Venus experienced a runaway greenhouse effect. The ocean evaporated, boiling into the atmosphere. Carbon dioxide baked from the Venus crust into the atmosphere. There is no going back. Venus is permanently outside the habitable zone, locked forever in a hellish greenhouse with a surface hot enough to melt lead. Earth is now near the middle of the habitable zone. Earth can never freeze over again. The sun is now too bright, and humans have added greenhouse gases to the atmosphere. A runaway greenhouse effect will not occur naturally on Earth for several billion years. But if we burn all fossil fuels, including tar sands and oil shale, it is conceivable that we will hasten a runaway greenhouse effect. How will climate change this century? It depends. It depends mainly on how much carbon dioxide humans put into the atmosphere. Our understanding of climate change is based most of all on Earth's history, how the climate responded in the past to changing boundary conditions such as atmospheric composition and surface properties. Ongoing global observations are also valuable, showing how climate is responding to rapid changes of atmospheric composition. Climate models in theory are helpful in interpreting what is happening, and they are needed to predict future changes. Why should we be concerned about human-made climate change? There have been huge climate changes in the past. Is today's climate the best one? These are reasonable questions. Indeed, they were statements made on National Public Radio in 2008 by my boss's boss's boss, boss's boss, the NASA administrator. Earth's climate history helps us answer such questions. This is the deep ocean temperature over the past 65 million years. 50 million years ago, Earth was warm. There were alligators in Alaska. The Arctic was tropical-like. There were no ice sheets, and sea level was 75 meters, 150 feet higher than today. Earth cooled over the past 50 million years. About 34 million years ago, it became cool enough for an ice sheet to form on Antarctica. What caused the great warmth in the first half of the Cenozoic era, and why did Earth then become cooler? The climate change was due mainly to change of atmospheric carbon dioxide. Climate forcings, perturbations of the planet's energy balance, must be due to changes of the energy coming into the planet, changes within the atmosphere, or changes on the surface. The sun's luminosity increased 0.4% over this period, which is a forcing of 1 watt per square meter. The continents at the beginning of the Cenozoic were already close to their present latitudes, so the surface forcing was only about 1 watt. But atmospheric CO2 varied from as little as 170 parts per million to more than 1,000, a forcing of more than 10 watts per square meter. The amount of CO2 naturally in the atmosphere-ocean system depends on the balance between the source and sink of CO2. The balance changes over time, depending mainly on continental drift. The source of CO2 is volcanic eruptions, which occur as moving continents subduct ocean floor beneath them. The metamorphosis of carbonates on the ocean floor into denser rocks due to high pressure and temperature as the continent rides over the ocean floor releases CO2 via volcanoes. The main sink of atmospheric CO2 is the weathering process, as sediments are carried by rivers to the ocean and deposited as carbonates on the ocean floor. Between 60 and 50 million years ago, as I showed on the last chart, between 60 and 50 million years ago, atmospheric CO2 increased rapidly because India was moving at high speed, about 20 centimeters per year, through the Tethys Ocean. This is India. Now the Indian Ocean, which had long been the depot center for major rivers and thus had a carbonate-rich ocean floor. When India crashed into Asia, pushing up the Himalayas and Tibetan Plateau, the source of CO2 diminished and the weathering sink increased, so atmospheric CO2 decreased and the planet cooled over the past 50 million years. The lesson from the Cenozoic is that the amount of CO2 in the atmosphere-ocean system changes naturally via exchange with the Earth's crust. The imbalance between the source and sink of CO2 yields a change of atmospheric CO2 of the order of 100 ppm in 1 million years, or 1/10,000th of a ppm per year. Humans are now increasing CO2 by about 2 ppm per year, 10,000 times faster than the natural geologic change. The Cenozoic also allows us to estimate that an ice sheet began to form on Antarctica when CO2 had declined to about 450 ppm. Some scientists estimate a higher amount of CO2 at that transition, but it is clear that burning all the fossil fuels would produce enough CO2 to lead Earth back toward the ice-free state, a different planet than the one that humans know. Climate also fluctuates on shorter timescales, as shown by this record of Antarctic temperature for the past 400,000 years. Civilization developed during the Holocene, the last almost 12,000 years, which is a relatively stable, warm period. During the last ice age, New York was under 1 kilometer of ice and sea level was 350 feet lower. The glacial to interglacial climate swings are caused by perturbations of Earth's orbit. As Jupiter, Saturn, and Venus tug at our planet, Earth's spin axis tilts successively slightly more toward or away from the Sun. Also, Earth's orbit becomes more or less eccentric. These changes alter the amount of sunlight striking the ice sheets in the summer. As ice sheets melt, they expose a darker surface that absorbs more sunlight, causing Earth to become slightly warmer. The warming ocean releases CO2 to the atmosphere, and the greenhouse effect of this CO2 causes additional warming. Changing ice sheet size and changing atmospheric CO2 are slow feedbacks that amplify the climate change. Indeed, these feedbacks cause almost the entire temperature change. The sea level record in the top curve tells us how large the ice sheets were. Greenhouse gas amount is also known from bubbles of air trapped in the Antarctic ice sheet as snow piled up. Multiplying the ice sheet plus greenhouse gas forcing by a climate sensitivity of 3/4 degrees Celsius for each watt of forcing yields good agreement with the actual climate change as shown by the lower curves. This empirical climate sensitivity includes all fast feedback processes, such as changes of water vapor, clouds, sea ice, and aerosols, and it is much more accurate than can be obtained from climate models. The climate sensitivity for a specified greenhouse gas change becomes twice as large if we wait long enough for the ice sheets to respond. The climate sensitivity and response time of the climate system are important because humans have caused greenhouse gases to increase in the past century far outside the range of the past several million years, as shown by the expanded timescale on the right. Earth has begun to warm, as shown by the lower curve, but much of the warming is still in the pipeline due to the long climate response time. To understand modern climate change, we must know all climate forcings, that is, perturbations to Earth's energy balance. Greenhouse gases are accurately measured. They cause a large positive warming forcing. Human-made fine particles in the air, aerosols, reflect sunlight and thus cause cooling. But it is very uncertain because it is not measured. Natural forcings due to the sun and volcanoes are probably larger now than they were in the 18th century, when the sun is believed to have been slightly dimmer and volcanic eruptions were greater. But the natural forcings are small compared to present human-made forcings. The net climate forcing is probably between +1 and +2 watts per square meter. Carbon dioxide is the largest forcing, and as time goes on, it will be more and more dominant because of its long lifetime in the atmosphere. In my University of Iowa talk in 2004, I used this photo of my daughter's children to discuss climate forcing. Sophie explains that the net forcing is about 2 watts, equivalent to 2 tiny light bulbs over every square meter of Earth's surface. But Connor could only count 1 watt. Connor may be right. We are not measuring aerosol forcing well enough to know for sure. So I went back to Sophie and Connor a few years later, when they were older and wiser. I asked them, what is the net climate forcing? They said they don't know. Well, we can't blame them if we adults fail to make the measurements. But my grandchildren were useful in another way. They forced me to keep speaking out. I decided I didn't want my grandchildren in the future to say, Opa understood what was happening, but he never made it clear. The upper graph shows estimates of changing climate forcings over the past century. Greenhouse gas forcing becomes increasingly dominant. Aerosol forcing is very uncertain because it is not well measured. If we use these forcings in a climate model with equilibrium sensitivity 3/4 of a degree per watt of forcing, we find good agreement with observed global temperature, as shown in the lower graph. This agreement could be partly accidental. If we used a model with greater sensitivity and a smaller climate forcing, or vice versa, we might also get agreement. However, the model's sensitivity agrees with the fast feedback climate sensitivity implied by paleoclimate data. The most fundamental check of the physics is the planet's energy imbalance. We anticipate that the planet is out of balance, with more energy coming in than is emitted to space. That imbalance is the signature of the greenhouse effect, the smoking gun that can confirm climate change is being driven by a forcing. Imbalance is expected because greenhouse gases reduce the planet's heat radiation to space. How can we measure Earth's energy imbalance? Small amounts of energy go into warming the atmosphere, melting ice, and warming the upper tens of meters of the ground, but most of the excess energy must go into the ocean, which has enormous heat capacity. Measuring the ocean's heat content accurately has been a great challenge, but the data are improving as more than 2,000 Argo floats have been distributed around the world ocean. Each float regularly yo-yos an instrument package to a depth as great as 2,000 meters. The best data covering the past 6 years indicate that the planet is out of energy balance by at least 1/2 watt per square meter. These data are for the time of minimum solar irradiance in the 10 to 12-year solar cycle. Our climate model yields an imbalance of 3/4 of a watt averaged over the solar cycle. I expect we will find close agreement with the model as the observations extend over the full solar cycle and the entire ocean. The data already show that the planet is out of energy balance, confirming the expected effect of human-made greenhouse gases. Global observations reveal effects of Earth's energy imbalance. The area of Arctic sea ice began to be measured by satellites in the late 1970s. The area of sea ice at the end of the melt season has decreased about 30%. There are year-to-year fluctuations because of the planet's energy imbalance. The area of sea ice will continue to decrease on decadal timescales. Unless we restore the planet's energy balance, we can expect to lose all of the late summer sea ice within the next few decades. The area on Greenland that has summer snowmelt, shown in red, fluctuates from year to year depending on the weather. But the melt area has increased about 50% over the past few decades. Meltwater runs to a low spot on the ice sheet and burrows a hole, a vertical shaft that goes all the way to the base of the ice sheet. This water lubricates the base of the ice sheet, and increased meltwater is one of the processes speeding up discharge of giant icebergs to the ocean. The net effect was once uncertain, but because global warming also increases the amount of water vapor in the air, so snowfall over the center of the ice sheet is increasing. But beginning in 2002, the gravity satellite GRACE began making measurements of Earth's gravitational field with such high precision that we can measure the change of ice sheet mass. The Greenland ice sheet gets heavier in the winter as snowfall piles up and loses mass, and it loses mass in the melting season. But Greenland is now losing more than 200 cubic kilometers of ice per year. Antarctica is losing more than 100 cubic kilometers per year. The data suggest that the rate of mass loss may be increasing. Another expected effect of global warming is expansion of subtropical dry regions. The overturning circulation, the rising air in the tropics with subsidence in the subtropics, which gives rise to the dry subtropics, is expected to expand poleward as the planet warms. Observations show that expansion by 4 degrees of latitude has occurred, averaged over all longitudes. The expanding subtropics affects the southern United States, the Mediterranean region, and Australia, for example. It is one of the reasons that Lake Mead and Lake Powell are only half full. The expanding subtropics is also one of the reasons for the increase in fires in the western United States, Greece, and Australia. With the changing climate, the fires burn hotter, making it more difficult for forests to recover. Another impact of global warming is the worldwide recession of mountain glaciers. Glaciers are receding in the Rocky Mountains, the Andes, the Alps, the Himalayas. Glacier National Park in the United States will need a new name within 25 years because it will have no glaciers if greenhouse gases continue to increase. Loss of glaciers has a practical impact because in the driest months, more than half of the water in major rivers, such as the Indus and Brahmaputra, is provided by glacier meltwater. Without glaciers, floods from spring snowmelt will be greater, and rivers will tend to run dry in the driest months. Coral reefs are the rainforests of the oceans, home to more than a quarter of ocean species. Coral reefs are under stress for several reasons. Two of the most important stresses are the warming waters and ocean acidification. Warming can cause coral bleaching and death as the coral expel their symbiotic algae. The ocean becomes relatively more acid as it takes up carbon dioxide, which is a problem for animals with carbonate shells or skeletons. If the water becomes too acid, it can dissolve carbonates. Such phenomena help us assess the atmospheric carbon dioxide amount required to maintain life on our planet as we know it. Each of these phenomena, including their responses to current levels of atmospheric CO2, lead to the conclusion that the target atmospheric CO2 amount that we must aim for is less than the current amount, which is 389 ppm in 2010. The best, most quantitative assessment is the need to restore planetary energy balance. Stabilizing climate, stopping global warming, requires restoration of Earth's energy balance. As long as there is more energy coming in than going out, the planet will keep getting warmer. The present imbalance is at least 1/2 watt per square meter. A 1/2 watt increase of thermal emission to space can be achieved by reducing atmospheric CO2 by 35 to 40 ppm. The optimum CO2 may be somewhat less than 350 ppm, especially if there are future reductions in atmospheric aerosols. However, adjustments of other forcings, such as methane and black soot, can help balance such effects. For policy purposes, all we need to know for the foreseeable future is that the CO2 target must be less than 350 ppm if we wish to preserve creation, the planet on which civilization developed. Bill McKibben and the young people who form the backbone of the organization 350.org have done a remarkable job of publicizing the need for this target. They have succeeded in getting more than 100 nations to agree to this target. What is the practical implication of less than 350 ppm? This chart shows the amount of carbon in fossil reservoirs, dark purple areas being the portion that has already been burned and released into the air. There is a range of estimates for the remaining reserves, which depend on part on whether we will go after every last drop. In order to stop growth of CO2 and return to a level below 350 ppm, we must phase out coal emissions rapidly and leave most of the other fossil fuels, the unconventional fuels such as tar sands, in the ground. In that case, atmospheric CO2 could peak at a value between 400 and 425 ppm, depending on how much of the remaining oil and gas we exploit. If we do not go every after every last drop of oil and gas, it will be possible to get CO2 back below 350 ppm within several decades, provided that we also adopt improved agricultural and forestry practices that cause CO2 to be stored in the vegetation and soil. So it is possible to achieve the 350 ppm target, but there are three essential actions. First, coal emissions need to be phased out rapidly. Second, the unconventional fossil fuels should be left in the ground. And third, we should not pursue every last drop of oil and gas. In other words, we must move on to the clean energy future now rather than using up all of the remaining fossils. But what is actually happening? The United States has signed an agreement with Canada for a pipeline to carry tar sands oil to Texas. New coal plants are being built all around the world, some being financed by the World Bank. Environmentally destructive mountaintop removal continues. Oil is pursued in pristine places. The environmentally destructive practice of shale fracturing is being developed and implemented to find the last bits of gas. There is a huge gap between government rhetoric and policy reality. Leaders say we have a planet in peril, yet their proposed policies barely differ from business as usual. Greenwash is plentiful, but the leaders follow a path of appeasement of fossil fuel special interests. There is no Winston Churchill willing to stand up and tell the truth about what is needed. International agreements are jury-rigged to allow continued business as usual. For example, the World Bank is allowed to finance new higher efficiency coal plants in developing countries and count these as clean development mechanism, which allows dirty plants in developed countries to continue. Total CO2 emissions actually increase. The science requirement is that the coal be left in the ground because fossil fuel stays in the atmosphere-ocean system for millennia. It does not help to burn it more efficiently. CO2 emissions were increasing 1.5% per year prior to the Kyoto Protocol. Subsequently, emissions have increased 2.5% per year, even with the recent economic downturn. Fossil fuel use continues to increase because fossil fuels are the cheapest energy. It is as certain as the law of gravity. As long as fossil fuels are the cheapest energy, their use will continue. Fossil fuels are cheapest in part because they are subsidized, but mainly because they are not made to their cost to society. Impact on human health, on the environment, and on the future of young people. The solution is obvious. Remove a rising price on carbon, a fee collected typically from the fossil fuel companies at the mine or port of entry. Regulations are also needed, as is technology development, but the success of these depends on having a rising carbon price. The public will accept a substantial rising carbon fee only if the money is distributed to the public. But the consumer place choose citizens sources to reduce their carbon emissions will soon be getting their green check. Carbon fee or tax is the only viable. It requires mainly that the United States and China agree upon a carbon price. I think Europe and Japan would surely consent. Any country not agreeing would have a tax made with fossil fuels. Cap-and-trade, in contrast, is favored by big banks and fossil fuel interests. In a multi-trillion-dollar carbon market, it is impossible to avoid bank involvement. Their highly skilled, secretive trading units would make billions without providing any added value. Cap-and-trade is proven to be ineffectual in reducing emissions, and it cannot be made global. India and China would never accept caps on their economies, nor should they. Fee and green check puts money in the public's hands, a lot of money, stimulating the economy and stimulating innovation. It is the fastest route to a clean energy future. It would quickly bring mountaintop removal and tar sands development to an end. It may be the only way to do that, surely the least painful way. Now, back to the basic issue. Stabilizing climate is a matter of intergenerational justice. Jake, my son's first child, recently was excited to have a baby sister who was 2.5 days old in this photo. My parents lived about 90 years. So Jake and Laura and Emma are likely to be around most of this century and feel the full force of climate change. Jake likes to protect his baby sister, even though she is sometimes a nuisance. Jake is a gentle giant for his age. If you believe long extrapolations, the charts suggest that he may be almost 2 meters tall eventually. But here is the problem. Protecting Laura and Emma may be out of Jake's control, no matter how big and strong he is. Today, we have pushed the planet close to tipping points. Ice is melting in the Arctic, on Greenland and Antarctica, and on mountain glaciers worldwide. Many species are stressed by environmental destruction and climate change. If fossil fuel emissions continue unabated, sea level rise and species extinction will accelerate out of humanity's control. Increasing temperature and atmospheric water vapor will magnify climate extremes, both droughts and floods. And the storms of our grandchildren will be much more devastating. Such intergenerational injustice is foreign to most nations, cultures, and religions. Yet we are saddled with governments who do nothing effective. They think they can set emissions at whatever level they choose. And they choose it with the help of fossil fuel industry. This situation is likely to continue until the public demands that governments do their job. But prospects for pressure from the public have been diminished by an effective campaign to discredit science by those who prefer business as usual. Yet I see two reasons for some optimism. First, China seems capable of making rational decisions and taking action. China has several incentives to move as rapidly as practical into clean energies. First, their high levels of local air and water pollution. Second, the fact that they will suffer more from global warming than most nations. And third, the economic advantage that they will gain by being out front in clean energy technologies. Indeed, China is aggressively investing in clean energy technologies. Will this action by China stimulate the United States and other nations to get moving? Maybe, but because of the undue influence of money in Washington and other capitals, I believe it is essential to involve the judicial branch of governments. As in the case of civil rights, achievement of justice probably requires people standing up for their rights and courts enforcing it. Legal scholars point out that governments have a fiduciary ability to manage the atmospheric. The executive and legislative branches of our governments are turning a deaf ear to the science. Courts have the ability to make emission reductions that the science shows to be necessary. Stabilizing climate is a matter of intergenerational justice that can be enforced. Young people and older people who support them must unite in demanding an effective approach that preserves our planet. I look forward to working with young people and their supporters in developing the scientific and legal case for young people and the planet. To the young people, I say, stand up for your rights. Demand that the government take the actions needed to assure a future for you and your children. To the old people, I say, we are not too old to fight. Let us gird up our loins and prepare to fight on the side of young people for protection of the world that they will inherit. Thank you.